Hello everyone, my name is Hua Dong, a postdoc researcher from TU Delft, the Netherlands. Today I'm here to give a talk on dry shrinkage of alkali-activated slag concrete with natural or recycled aggregates. First of all, let's have a brief overview of construction and demolition wastes. They contain a wide variety of materials such as concrete, bricks, wood, glass, metals, and plastic. According to European Commission, about 450 to 500 million tons of construction and demolition wastes are generated every year in Europe. At least a third is concrete. In recent years, recycled aggregates take up 12% of the total amount of aggregates used in construction field. This is a way how the recycled aggregates contribute to a sustainable society by reducing dependence on primary raw materials. Why alkali-activated concrete, or shortly AAC? We know that AAC is a cement-free concrete, and the raw materials can be industrial byproducts like blast furnace slag, fly ash, the different kinds of alkali activators. Concerning that, the aggregates account for 70 to 80% of the volume of concrete. So incorporating recycled aggregates from construction and demolition waste in alkali-activated concrete will further contribute to a sustainable society. Alkali-activated concrete has multiple advantages. For instance, good mechanical properties, chemical resistance, and fire resistance. Of course, it also has some weak points, possibly high shrinkage and creep. Another critical point is that most chemical admixtures developed or used for conventional concrete will not function properly in alkali-activated concrete due to its high alkalinity. The aim of this study is to investigate the influence of recycled aggregates on workability, strength, dry shrinkage, mass loss of slag-based alkali-activated concrete. The results will be compared with that of conventional concrete. Raw materials. Conventional concrete was prepared with cement, sand, natural or recycled aggregates, while alkali-activated concrete was prepared based on two Rylan mixtures, with BFS as precursor, sodium hydroxide and water glass as activators, sand, natural or recycled aggregates. First of all, the recycled aggregates from construction demolition wastes have been characterized. They mainly consist of crushed concrete and unbound gravels with a water absorption capacity of around 5%. The recycled aggregates were pre-saturated with water before mixing with other raw materials. For the mix design, two strength classes were considered. They are low strength concrete and moderate strength concrete. For each strength class, both conventional concrete and alkali activated concrete were prepared, either with natural aggregates or recycled aggregates. After demolding, the specimens were subjected to sealed curing at 20 degrees Celsius until testing. Compressive strength, dry shrinkage, and mass loss of the specimens were tested according to relevant standards. Here we have the results. In general, concrete mixtures with recycled aggregates had lower slump values than that with natural aggregates. This can be explained by the angular shape of recycled aggregates in comparison with the round shape of natural aggregates used in this study. We can see that the incorporation of recycled aggregates reduced compressive strength of both conventional and alkali activated concrete. The reason can be the porous structure of recycled aggregates. Moreover, for alkali activated concrete, the extra water used for pre-saturation of recycled aggregates might have diluted the alkali solution and then reduced the concrete strength. Note that the negative effect of recycled aggregates on compressive strength was smaller for low-strength concrete than for moderate-strength concrete, because the role of mortar strength is high in low-strength concrete, and the role of aggregates becomes higher for concrete with higher strength. This slide shows the mass loss and drying shrinkage of concrete specimens. In the first figure, we can see that the mass loss of the specimens under drying was greater for low-strength concrete than for moderate-strength concrete. It is also greater for concrete with recycled aggregates than that with natural aggregates. The second figure shows the drying shrinkage value. It is worthwhile to point out that the alkali-activated concrete with natural aggregates had a lower shrinkage value than conventional concrete with a similar strength class. It means alkali-activated concrete doesn't necessarily have a higher drying shrinkage than conventional concrete. From the second figure, we can also see that the incorporation of recycled aggregates in alkali-activated concrete increased the drying shrinkage. One reason can be that the recycled aggregates increased the total paste content in concrete and increased the drying shrinkage. For conventional concrete, low-strength concrete had a higher drying shrinkage than moderate-strength concrete. On the contrary, for alkali-activated concrete, low-strength concrete had a lower drying shrinkage. The main reason is the higher amount of alkali activators used in moderate strength concrete, because a more alkali activator may result in a finer pore structure. In the finer pore structure, high tensile stress may develop under drying. The last figure shows the relationship between mass loss and drying shrinkage. For the concrete with natural aggregates, moderate strength concrete exhibited a steeper curve compared with low strength concrete. At a certain mass loss, the lower drying shrinkage of low strength concrete can be explained by the fact that the water loss mainly took place in large capillary pores. Thus, a lower tensile stress was generated in the pores. It is also interesting to see that the curves of conventional concrete almost coincided with that of alkali-activated concrete when natural aggregates were used. It implies that for concrete with natural aggregates in this study, reaching a certain drying shrinkage was a matter of time, just depending on the point when a certain mass was lost. In the last figure, we can see a big difference in the curves between alkali-activated concrete made with natural aggregates and that made with recycled aggregates. To reach the same drying shrinkage, more water is lost from alkali-activated concrete made of recycled aggregates. Again, this can be explained by the pore structure of concrete. Besides the drying shrinkage values, it is also important to check the consequence of the drying shrinkage. In this study, after 3 days exposure to drying, we could already see the surface cracking on alkali-activated concrete, while no obvious cracking was observed on conventional concrete. Surface cracking became more obvious when recycled aggregates were used. In fact, the surface cracking due to drying is the common problem for alkali-activated concrete at early ages. The mechanism can be very complex. To understand the mechanisms, many factors need to be considered. For instance, the characteristics of reaction products, pore structure, micromechanical properties of reaction products, moisture transport in concrete, internal restraint due to aggregates or external restraint, and so on. Some strategies have been proposed to mitigate drying shrinkage cracking of alkali-activated concrete. For instance, replacement of BFS with fly ash using the alkali activator with lower silicate content, or most practically a sufficient curing. All these points are very important for promoting the use of recycled aggregates in alkali-activated concrete and need to be considered. in future study. Here we have the summary. Due to limited time, I will skip this part. If you have any questions, please feel free to ask. In the end, I would like to thank you so much for your attention.